Okay, welcome everyone. So it's a great pleasure to welcome Professor Howard Wiseman from Griffith University, Brisbane, to give today's ICTS distinguished lecture. So this is as part of the Quantum Trajectories meeting. So Professor Howard Wiseman is an Australian theoretical quantum physicist, best known for his work in quantum information, quantum foundations, and quantum measurement and control. After completing his PhD at the University of Queensland in 1994, he did a postdoc at the University of Auckland before returning to Queensland in 1996. He has been at Griffith University since 1999 and has been the director of the Center for Quantum Dynamics since 2007. Professor Wiseman has won several Australian medals and prizes for his physics research and was the senior author of a paper that won the 2023 Ehrenfest Award for Quantum Foundations. The paper has a very interesting title, A Strong No-Go Theorem on the Wigner's Friend Paradox. Professor Wiseman has been elected a Fellow of the Australian Academy of Science and American Physical Society and the Optical Society of America. Together with Gerard Wilburn, Howard has a very popular graduate level textbook called Quantum Measurement and Control. It's a great book for introduction to quantum measurement theory, open quantum systems, quantum trajectories, and feedback and control, and so on. So today, Howard will talk about are we living in the matrix, what quantum experiments reveal about the world and our powers in it, and what the future may hold. Actually, so yesterday I watched the movie Matrix.
Oh,
so
right.
and I found out actually that it's a series of movies, and one has to watch all three to understand. But
Three,
yeah,
four?
so welcome, Howard.
Thank you, Abhishek. It's a great honor to be giving this lecture. So I decided to start with this slide because you might recognize this was the picture that was used for advertising. It's on the poster outside, but this is showing a little bit more of it. So I hope to maybe sucker in some people who might not otherwise come by, making this look like I'm a particle physicist. Because I know that ICTS is has broad research in theoretical sciences. I assume there are particle physicists here. So yes, anyway, I'm glad for whoever turned up. But of course, I'm not actually a particle physicist. So I'm a theoretical quantum physicist. And yes, my university, Griffith University, is here in Southeast Queensland. But there's another reason that I chose to give this as my profile picture, if you like, for this talk. And that's because there was a physicist who was working at CERN whose work was very central to what I'm going to be talking about today, and that's John Bell. And we'll be getting to his work eventually. Okay, so the other things I guess I wanted to say before getting to the talk proper is that yes, obviously this is part of the Quantum Trajectories program, but I won't really be talking about quantum trajectories here at all, but it does fit, as we'll see, in sort of the other parts of the program on quantum computing, for example, will come in later in this, in the talk. Oh, that's right. And then the final thing I wanted to say is that most of this talk is pitched at a level which is very basic, or at least might seem very basic. And so for anyone who's thinking, oh yes, I know all this, I hope at least that you might get some inspiration about what would be good ideas about communicating things, trying to communicate things in a simple way. But then definitely in the latter part of the talk, I'll be getting on to things which are probably not familiar to many people. And so you should wake up for that at the very least. Okay, so yes, the title of my talk, the very long title for my talk is, Are We Living in the Matrix? What Quantum Experiments Reveal About Our World, the world and our powers in it, and what the future may hold. Not a great title, I know, but yeah, we'll see. And so these other things are just all the funding bodies that have supported the work in recent years that I'll be talking about towards the end. Okay, so yes, as Abhishek says, the necessary background that I'm assuming is everybody has watched the Matrix movies. Now, I know that actually these movies go back, the original one goes back a long time, before half the people in this room were born, probably. But nevertheless, it's got a bit of a cultural longevity, and a new movie came out just a few years ago, so I hope that inspired some more people to watch it. And it doesn't really matter if you haven't seen it. The most important thing to take, that you need to know about the movie, the first movie, let's say, is that the postulate of the movie is that there is a hidden level of information processing, at least this is the postulate that is going to be relevant to what I'll be talking about, that underlies all that seems to be real, but which is actually an illusion. Okay. So, how could you tell if you are living in a world like that, where actually, what seems to be real is actually an illusion? Well, in the movie, it's because there exist these agents who can break the normal rules of reality, break the rules that would apply if they were living in the real world. And in the movie, you can undergo a transformation, choose the right pill, and learn to be like these agents. So the message of this talk is that you are living in the matrix. These agents really do exist. We are called quantum physicists, and you can learn to be like us. Okay, so this is the story that I'm going to tell. To begin with, and you'll see that the matrix is going to turn up all over the place with slightly different meanings. I'm going to start by talking about how the mechanics of the matrix was discovered, and how this lets us break the normal rules of reality, and how we can think of that breaking the rules as really testing for the existence of this hidden level of information processing. Then I'll talk briefly about how we can harness these superpowers that we agents have for the good of mankind. And then in the last, where I'll be talking about the new work, where I'll make a link with the latest Matrix movie and the idea of experimenting on agents in the Matrix in yet another sense. Okay, so I heard some chuckles already about this discovering of the mechanics of the matrix, and that's probably because they knew that what I was going to talk about was this discovery here in 1925, the formulation of matrix mechanics. So this is, yes, from a textbook, and everybody probably knows it's the 100-year anniversary of the discovery of quantum mechanics, or matrix mechanics, as some people called it back then. So, of course, it was Heisenberg who's specifically associated with this idea, this term. And so I'll let him tell the story in my own words. So this is not a direct quote from Heisenberg, okay? You can tell by the font that it's a paraphrase. Okay. Heisenberg, would you believe that by thinking about the emission of light from atoms, I came up with the radical idea that a physical quantity like position or velocity should not be represented by a number, but rather by a matrix of numbers. In fact, often an infinitely large matrix. And then using this idea, he says, it has become possible to derive properties of atoms like their quantized, in other words, discrete energy levels. Some people call this idea matrix mechanics. I prefer just quantum mechanics. That actually was Heisenberg's point of view. But anyway, I'm making the play on matrix mechanics. So this was a radical idea, as Heisenberg recognized, and initially it wasn't clear at all what these matrices meant. How could they possibly relate to reality? They were good for calculating spectra, but how could they relate to anything more directly? And so it was a couple of years later with his older colleague Niels Bohr in Copenhagen that these two got together and came up with what became known as the Copenhagen interpretation. And so again, a rough paraphrase of that, Heisenberg explaining the matrix representing, for example, the spin of an electron, there's an example, tells us only the possible values we may find if we measure it. Before the measurement, the spin has no value. It's just represented by this matrix. It is the act of measurement itself which creates the measured value. In this case, plus or minus 1/2. And Bohr, who developed it more philosophically, saying, in other words, our understanding of reality in the macroscopic or classical world does not apply to the microscopic or quantum world. The nature of the quantum world cannot be understood. So this was an even more radical position to take now. This is making actual statements about physics, not just about mathematics. And not surprisingly, not all physicists agreed with this interpretation. And the most famous one, of course, was Albert Einstein. And he had, again, some dialogues with Bohr over many years. And again, I'm just going to distill all of those down to some cartoon depiction of this dialogue. So Albert saying, I just can't accept your interpretation, Bohr. Bohr, why not, Einstein? First. Okay, and so here these things which are in a different font and underlined really are quotes from Einstein. So it says, first, physics should represent a reality in time and space so that we can understand it. Second, a physical theory should not give a special role to measurement. What even is a measurement? Will a sidelong glance by a mouse suffice? He asked. Third, he says, your theory has a weird sort of non-locality in it, a spooky action in the distance whenever two particles are entangled and one is measured. And then Einstein's conclusion was that a more complete theory, a theory with hidden variables defining physical quantities that would give a picture of reality in space and time, which would not require a special role for measurement because measurement would just reveal those values, and which would remove this spooky action at distance. Yeah, I think I got that sentence all mixed up. That all those problems would be fixed basically by introducing some sort of hidden variables theory. So there was this huge disagreement between Einstein and Bohr, and then basically nothing happened. Okay, that was in 1935, and for essentially a generation, physicists just more or less forgot about that debate because they were busy doing the things that physicists were busy doing in the middle years of the 20th century, discovering a lot of things, building things, and then of course, some things did happen. I'm simplifying the story a great deal, but then in 1964 was when this bombshell dropped from John Bell, the physicist that I mentioned before, working at CERN. And so again, in cartoons, what he said is that I have proven a theorem showing that at least Einstein's third argument fails. So in other words, the argument against Copenhagen interpretation based on non-locality, Bell is saying that that argument of Einstein doesn't work. The reason is that any theory, Bell proved, any theory that gives the same predictions as quantum mechanics, even if you add hidden variables, for example, will have spooky action at a distance, the thing that Einstein was worried about. Specifically, to put it more definitely, quantum mechanics predicts correlations between measurement results on distant entangled particles that cannot be explained without non-locality. In other words, without faster than light causal influence. But that's just a statement about quantum mechanics predictions. And at that point, in 1964, the particular predictions that Bell considered in his theorem had never been measured experimentally. No one had done the experiment. And for good reason, that it was a very difficult experiment for the time. So Bell was of the opinion that this prediction, therefore, of quantum mechanics is a very strange prediction because it proves that there are these correlations that cannot be explained without faster than light causal influence, even though we know, of course, that we can't signal faster than light in quantum mechanics. So this is exactly why it's spooky in Einstein's sense, or very strange, as I'm saying here. So Bell was of the opinion that we should do experiments, therefore. We should test to see whether these quantum mechanical predictions really do exist. Is the universe really that strange? And so this is, getting on to section 2 then, this is breaking the normal rules of reality. We think the normal rules of reality are that we should be able to explain correlations by local effects without having causes going faster than light. then this is an experiment that is going to break that reality. And I've just stolen this picture from somewhere else because it fitted in. Okay, so the story of what happened is probably well known to everyone, especially because there was a Nobel Prize in Physics given a couple of years ago for it. There were then what are now known as Bell experiments because he inspired them from 1973 to 2015. So beginning with John Clauser, so he's saying here, so in fact even before then, he's saying in 1969, I helped develop the theory which made Bell's idea truly testable. And then in 1973, I performed the first Bell experiments using photons. And then Alain Aspect is saying, I closed a loophole by including fast switching of the settings while the photons were in flight in 1982. And finally, Anton Zeilinger, I made further advances in the theory and experiment, closing more loopholes. You think this is to do with loopholes, culminating in what is widely regarded as a definitive Bell experiment in 2015. And of course, many of you know that there were in fact 3 definitive experiments performed almost simultaneously in 2015. I'm just going to give a picture relating to one of them. So this is the first author on the experiment that was done in Anton Zeilinger's group in Vienna. It's Marissa Justina, and so I'll give her the honor of explaining what happened. So I'm sure you're all wondering, did we see a violation of the well, I haven't talked about it. Did we see the correlations that Bell talked about? So is this Bell non-locality real? Or is quantum mechanics actually going to be wrong, which is what Bell hoped, okay? Because it's always more exciting to disprove a well-established theory than to verify its predictions, even if those predictions are very strange. So yes, as I'm sure you guess, here's the result. Okay, so to summarize how the experiment was done, we created pairs of entangled photons and sent them to 2 labs more than 50 meters apart. So this is actually a picture of the corridor where the experiment was performed. So this is one measurement apparatus here, and the other one is down the other end of the corridor. There we performed at precisely the same time measurements of the spin of the photons in certain directions. So just as I talked about with spin before, each measurement gave one of 2 possible values, and that these values in the 2 labs were correlated. But that's not the spooky thing. The spooky thing is that they were correlated in exactly the way that quantum mechanics predicts, and the way that which John Bell had used in his non-locality theorem. So in other words, Bell non-locality is real. Even though, as just to stress for public audiences, I always stress this, even though we cannot use these correlations to send signals faster than light. Okay, so what are these spooky correlations? How can we have, what could make correlations so weird that we could come to a conclusion, like that there must be something, causal influence going faster than light if we want to explain these correlations? So in some places, you'll hear the description that these correlations, these so-called spooky correlations, are like having 2 dice that no matter how far away, when you roll them, they always give the same number on top. Okay, I sometimes call that the new scientist explanation. But actually, that's exactly not what Bell correlations are like, okay? Because these correlations can be explained by a purely local mechanism, okay? Without any action in the distance, with nothing going faster than light, okay? If I had clever enough engineers, then I'm sure they could design a die like this with a motor inside and a clock that would, know that if this die is thrown at a particular time, it should come up, it'll move weights around inside the die to compensate for however it's thrown, to make sure that it comes up with a particular number on top, and the other die is got exactly the same mechanism in it, so whenever they're thrown at the same time, they will always come with the same number on top. That's physically possible, okay? It'd be extremely challenging engineering-wise, but it's not impossible. Okay? And so this is basically what Einstein thought quantum mechanics was like. There's something really complicated going on inside in particles that make them behave in this peculiar way, gives you these sorts of correlations, but there's got to be some way to understand it. So that's not what Bell correlations are, because they can be explained. So as I say, closed but no dice. So to identify Bell-type correlations, we have to, one correlation for which there is no possible mechanism which could give rise to those. It's more complicated than this, much more subtle. And so I'm going to attempt to explain it. So the easiest way I think of explaining it is to formulate the problem in terms of a game. So it's a game with just a single team of 2 players. They're playing against the referees, okay? And according to the normal rules of reality, in other words, local mechanisms, sometimes when they play the game, they're going to lose. But with the spooky quantum correlations, they can break those rules and win the game every time. So like the agents in the matrix, they have this super ability to do this. Okay, so in other words, I'm going to describe an experiment where we can, in some sense, show that the matrix exists. And we're going to do that by considering a matrix with a small m that can't. Okay, and so this is a version of Bell's theorem, which was published by P.K. Aravind in 2002. So he's saying, yes, Bell's theorem can be proven in many different ways. This is my proof. We consider a 3x3 matrix, just an ordinary matrix like this to begin, for which each of the entries is either a 0 or a 1, like that. Okay, very simple thing. So that's straightforward. What I want you to think about is a magic matrix. Okay, magic matrix has these properties, but it also has the properties that each column has an even number of 1s, and each row has an odd number of 1s. So why do I call that a magic matrix? Because it can't exist. There's always going to be at least one row or column that must fail. And can anybody tell me why? There are an awful lot of smart people in this room. I'm sure somebody can tell me why this magic matrix can't exist. Sorry?
It is square matrix.
It is square. It's a 3x3 matrix. Sorry?
Yeah, this is important.
Yeah, it is a 3x3 matrix, yes. It's that simple, yes. Yeah, and then why would that mean that it doesn't exist? But why is that a contradiction, though? It's a different matrix once I've transposed it. Yes?
You can count the total number of 1s by rows and get an even number, right? By columns and get an odd number.
Thank you. That's right, exactly. If you count, because then three lots of even numbers is an even number, but 3 lots of odd numbers is an odd number. So it can't exist. Okay. So this doesn't exist. Nevertheless, we can build a game around the idea of this magic matrix. And in this game, we have 2 players called Rowan and Colin. You might already guess where I'm going with this. Their job is going to be convince us, the referees, that they actually have a magic matrix. Now, we can't just ask them for the magic matrix because obviously it doesn't exist. So that would be a stupid thing to do. Right? That would be a very boring game. They could never win. So let's at least give them a fighting chance. We'll just ask Colin for 1 column and Rowan for 1 row. Right? And obviously when Cole gives his answer, there should be an even number of 1s because that's the constraint. And when Row gives his answer, there should be an odd number of 1s because that's the constraint on the rows. And of course, the entries should agree like that. So there's an example where they succeed by Cole saying 0, 0, 0 and Row saying 0, 1, 0, 0, 1, 0. When Cole is asked for the first row and Row is asked for the second column. Oh, did I totally screw that up? Yes. When Colin is asked for the first column and Row is asked for the second row. Okay. Now, but if we just have them sitting there in the same room with us and ask them like this, that's also a stupid, boring game, right? Because they can always win. So Cole, for example, could always just say 0, 0, 0, and Row can always say 2 zeros and a 1, and all he has to do is make sure that the 1 doesn't clash with the 0 for Colin. So that's no good as a game. Okay, What about this? We put col and rho in distant concrete bunkers to prevent any communication between them. So here they are, looking anxious. And now we have the interrogators who are going to ask them for one of the columns and one of the rows. They don't know which one they're going to get asked, but they have to answer. And in this case, again, they succeed, right? It's the same answer as before. But can they always succeed in this game? Well, if you think about it, what they have to do is, essentially the best thing they could do would be to decide beforehand how they're going to answer any given question. Right? Because otherwise there's just more randomness in the system. It's just going to be even worse for them, right? They could just accidentally put a 0 and a 1 in the same place. So essentially they would have to, like col would have to know all 3 columns he's going to say, and rho has to know all 3 rows he's going to say, but that would mean that they each have to know the whole matrix, and the matrix can't exist, right? So some of the time they're going to necessarily give incompatible answers, and in fact at least 1/9 of the time that's going to be what happens. So for example, here they're asked for column 2 and row 2. They tried the same ideas before, and this time it fails, okay, because there's a clash here. So we know that they don't actually have a magic matrix because they failed to the common element of the matrix is inconsistent between the two. So it seems like, right, we've got a cast iron proof that they have to lose this game 1/9 of the time. If you play it over and over, that's how often they're going to lose, at least that much time. But what if col and rho share one of these entangled pairs of particles that Einstein and then Bell talked about? Well, then it turns out, so I'll let Aravind say, if col and rho share pairs of entangled particles, they can win 100% of the time. And as far as we know, this works no matter how far apart they are or how thick the concrete is or anything like that, right? There's no communication between them, and they could be on different sides of the planet, and nevertheless, as far as we know theoretically, this still works. How is it done? Well, col and rho each need a device which can make 3 different measurements, because there are 3 questions they can be asked, on the one quantum particle which sits inside the box. And each of those questions can yield 4 possible different answers, which could be flashing light. So imagine that they've got these little devices on, like, hidden in their watches maybe, and the interrogators have dark glasses on so they can't actually see the flashing lights. And so they don't notice what's going on. And so, so if in this instance where col is asked for column 2 and rho is asked for row 2, they press the appropriate buttons on each of their devices. One of the lights flashes on each of them, and because they've memorized the code, they know col knows that a red flash means I should answer 110, and rho knows that a blue flash means he should answer 111, and you put them together and they're compatible, and they are always going to be compatible. Okay, they can win this game every time by using these measurements on entangled particles. So in other words, quantum entanglement lets them break the normal rules of reality. Now, if you're skeptical, you might think, no, this can't be right? Because if col, for example, made all 3 measurements, so he just pressed all 3 of his buttons, then the 3 answers he would get would let him write down the whole magic matrix, and the same thing with rho, right? But the magic matrix can't exist, we know that, so therefore what you've told me is, about entanglement just can't possibly be true. Well, obviously it is true, I'm not lying to you, and so correlations like this have been seen many times in experiment. So the resolution to the skeptical question is that col's 3 measurements are incompatible measurements. Once he's made 1 measurement on his particle, in other words, once he's pressed 1 button, then pressing the other buttons won't give anything useful at all. They just give complete random answers. Okay? So it only works once. You have to choose one of the 3 columns and for rho and one of the 3 rows. and then the device doesn't work anymore. That's it. Of course, you get a new device or do the same thing with the new pair of entangled particles. You want to play the game again. But with that particular pair, that's it. With that magic matrix, you only get to find out one column and one row. You just choose which ones you want. And so another way to put this is the reason that it works is that unperformed measurements have no outcomes, which is a quote from Asher Perez, who's a famous physicist. I'll leave it at that. Okay, so we've shown that agents can break the normal rules of reality by using quantum entanglement, in particular Bell correlations. Right? So they're demonstrating these superpowers, like that there's something hidden information processing going on, something weird, just like the agents in the matrix, right? So this superpower, proves the existence of the matrix in that sense. But you might say, yeah, but that's a very special game you just invented for them to win, right? It seems like a rather useless superpower. It's sort of like having the ability to fly, but when you're already on a jet plane. Right? But the game I gave you was a very specific game, but actually the general idea of quantum correlations like this is not so useless. So as a general point, entanglement lies behind lots of physical phenomena, so it's a topic of very great interest. But also specifically, we're now entering this age of quantum information technology where we're using these ideas to build useful things. And so, for example, Bell-type correlations can be used to enable absolutely secure communication between two agents. So in other words, we can totally rule out the existence of an eavesdropper. Entanglement allows the teleportation of quantum information across distances, again, not faster than light, but nevertheless without any intervening medium, which enables communication, could enable secure communication on a global scale then. And then finally, entanglement is also key to quantum computation, at least as far as we know. Which is useful for solving certain types of problems that in practice could never be solved on a conventional computer, and which I'm going to come back to in section 5. So this is just a little, illustration. The center I'm in at Griffith University, we have lots of different laboratories and theory, and this idea of entanglement and quantum information lies across a lot of them, and we're also part of, some of us are, like, I'm vaguely trying to indicate which ones, are also part of this Australian Centre for Quantum Computation and Communication Technology. So that's just my little ad for that. Okay, so that's counting down. Is that right? What does that mean? 25 minutes to go, including questions or? Excluding questions. Oh, okay, so I've been going a great rate. Right, okay, so I'm only halfway through and I'm up to the final section. You've been a great audience. You're so quick to pick things up. Okay, so part 5 is where I'm going to move on from Bell non-locality and on to some of the work that I've been doing more recently with colleagues. And so I'm tying it into the matrix theme by saying that this is the future that I'm envisaging, or we're envisaging, is experimenting on agents in the matrix. Okay, and so if you've seen the latest Matrix movie, which I said came out just a few years ago, that's more or less how this movie starts, with this idea that, actually is there some human outside who's all this long time has just been experimenting on simulated agents in a computer like this. Okay, so anyway, as I said, based on work by me and various collaborators, you can see some of those collaborators here. No, actually, that was just some art which was done for one of the popular journals that covered our work. So this is the actual work. So I guess the most important paper was this one published in 2020 in Nature Physics, which was referred to in the introduction. So a strong no-go theorem on the Wigner's-Friend paradox. So it has a lot of authors because it was a theory and experiment paper, but I'm not going to talk anything about this experiment. I'm only talking about the theoretical contributions. And on that topic, there are a couple of other theory papers that I've been involved in. And the common author on all of these works is Eric Cavalcanti, who's my colleague at Griffith University. Okay, yes, so in particular, what I'll really be talking about is the formulation which is in these two papers here, and there's another bit of art that got done for this work. Okay, but before I get on to that, what I want to do is go back and talk more about Bell's theorem, but be a bit more precise about what Bell's theorem really proves, okay, which hopefully a lot of you are having this question, like, he keeps talking about this non-locality, what does he really mean? Surely, I mean, there's more to it than that. And yes, there is more to it than that, okay. But we can be pretty precise about what Bell's theorem is, or in other words, or not even having to talk about Bell's theorem, we can say that Bell experiments, right, rule out a set of propositions about the world. So in other words, we can make these propositions about how the world might be, from them derive some inequalities, as it turns out, some restrictions on the correlations that could possibly be seen in nature under certain experimental conditions with parties, a long way away and being measured at the same time. But then we do the experiments and find that we break those restrictions. And so therefore we know that one of these propositions that we made to derive those must be wrong, okay? That's how Bell experiments work. And there are many different ways of formulating those propositions, but this is the way that's going to be particularly useful for the story I'm going to tell you, okay? So the way I'm doing it, there are 4 propositions. So the first one is I'm calling free setting. Sometimes it's also called free choice or setting independence, that sort of idea, is that an experimental setting, should be careful. This is a very specific way that I'm formulating it, but it's related to those ideas. An experimental setting, so in other words, how you set up your apparatus, what you choose to measure, for example, an experimental setting chosen in a manner appropriate for a randomized trial will be correlated with other experimental variables only if it is a cause of them. Okay, so it won't just be correlated with other variables for no reason. It would actually have to have a causal influence on those other variables in order to be able to be correlated with them. Now note that I'm using the word cause. I'm not actually defining the word, but it turns out that I don't need to define it because it's going to come up in several of these other propositions, and logically they fit together that I don't actually even need to define the word in order to draw the conclusions that I need. Okay. But it obviously I'm using the word with the intuitive meaning. Right. Relativistic causality, so there's causal appearing here. An event can only be a cause for events in its future light cone, which is a formal way of saying that causal influences cannot exceed light speed. Third one, which doesn't often get talked about, absoluteness of outcomes. It says the outcome of a measurement is absolutely real. So absolutely real just means not real in a relative sense. So not, for example, real only in this world, out of many worlds, or only for me, or things like that. Okay? So we actually, sometimes you hear like people who believe in the many worlds interpretation will say, oh, our theory is local, and despite Bell's theorem, well, yeah, you could say that, but if we put this assumption in explicitly, then, well, that solves that problem. Okay, we've got a watertight theorem again, and this will be what is broken in a many worlds interpretation. And finally, this is a crucial one, which I'll call causal explanation. So this goes to the heart of what we meant about explaining correlations or having a mechanism for correlations. Okay? The idea is that if two variables, so very roughly, it's that correlations implies causation. Right? But putting it in a more precisely, if two variables are correlated, then either one causes the other, or they have a common cause that explains the correlation. And by explaining the correlation, that's a specific mathematical sense that conditioning on the value of the common cause would remove the correlation. Okay, so this is how, well, Reichenbach was the person who introduced this idea, but yeah, it's how people who talk about causes think about, the way they normally work. Okay, so we can say that one of these things must be wrong because of Bell experiments. So you might ask, well, which one? Well, that depends who you ask, right? If we ask the ghost of Niels Bohr, I think I know what his answer would be that we should give up the last one. We should give up this idea of causal explanation. Because he's saying, this is what I've said all along. We should not try to explain what's going on within quantum experiments. We cannot understand the quantum world. What about his rival, the ghost of Albert Einstein? What would he say? Well, I think he'd say, I don't know. All of these propositions seem necessary to me to make sense of the world. Because I think that pretty clearly Einstein, would have held to all of those. So, right. So, chalk one up for Bohr, if you like. All right, so going back, so this is just to remind you, there they are again, all these propositions which are ruled out by Bell experiments. As a step towards what I want to tell you about, I want to slightly change things. Now, that was what have I done? Oh, okay, sorry. Yep. No, I'm just here, sorry, I'm not changing anything. I'm just making the conceptual point that the difference between what we know from Bell experiments and Bell's theorem is that Bell's theorem was formulated before the experiments were done. And so in a sense, you could say that Bell's theorem says that the following list of propositions cannot all be true, where we have to have the fifth proposition, which is just that the predictions of quantum mechanics are accurate. Right? So this is what Bell said in 1964 and said, you should go away and actually do the experiments and see whether the predictions of quantum mechanics are accurate. So once we've done the experiments, right, we don't need that. We can just talk about these other types of assumptions, which are sometimes called metaphysical assumptions, as opposed to physical assumptions like this, or even technological. Okay, so that's just to make the difference between experiment and theorem. Okay, now I want to make a change, right? Here, as a step towards what I want to talk about, is a slightly stronger version of Bell's theorem. And when we talk about a stronger version of a theorem, we mean a theorem which is using weaker assumptions. Right? So assumptions that say less about the nature of the world. They're assuming less about things. And so the crucial difference which I'm making here is, instead of talking about absoluteness of outcomes or measurements, I'm going to just talk about absoluteness of observations, where by observation I mean an observation made by a human being. Okay, so that's a weaker assumption, because I'm not saying anything about whether a device in the laboratory like a photodetector produces an absolutely real outcome, but I'm saying that when a human observes it, then surely it's got to be absolutely real. Okay, I mean, when I say surely, of course, not necessarily, right? You can question this, you can question everything, but it's a weaker assumption, right? Okay, and so the point is that if I weaken the assumption like that, then I can't anymore talk about the experiment, because this experiment has never been done. And the reason is that humans are much slower at observing things than detectors are. So a detector can make a measurement in a microsecond or something like that, whereas a human would take closer to 1/10 of a second. So if you want to do this experiment with the humans far enough away to rule out any influence faster than light, you would have to have one human on the moon, for example. Okay, much more difficult experiment. Should still be done at some point, but it's much more difficult. All right, but we still have a theorem if we say, include this, that the predictions of quantum mechanics are accurate, because the predictions would still say that, when the human observes it, they're going to see the same thing as when a detector observes it. It's not going to make any difference to the outcomes of the experiment. And so we have this stronger version of Bell's theorem, which is actually due to Adrian Kent, which I can throw out here because some people might know that name. But yeah, that's a step. Okay, so right, the crucial next step is this one. So this is the theorem in the 2023 version of it, which we call a thoughtful local friendliness theorem. Right? So it's the same sort of thing. It says that the following list of propositions about the world cannot all be true, but crucially, this one here, causal explanation, the thing that Bohr said we should give up, that's no longer an assumption. Okay, so all the other assumptions are the same, exactly the same: free setting, relativistic causality, absoluteness of observations, right? But we don't have this assumption of causal explanation at all, but what we do have is a new assumption, which I'm calling here friendliness, and it means friendly, yes, it comes from the Wigner-Friend paper, for those who know about that, but you can think of it as being friendly towards artificial intelligence. So if an artificial intelligence displays human-level abilities, their thoughts are as real as a human being's. Okay, so again, this is a proposition. Okay, I'm not saying that all these things are correct, and indeed, I'd be crazy to say that because we know by the theorem that they're not, right? But it's a reasonable proposition about the way the world could be that, well, we accept other humans as having thoughts that are as real as our own. Why shouldn't we extend that to an artificial intelligence that seems as, you know, as intelligent and reasonable as any of us are? So that's the assumption, friendliness. Causal explanation is no longer an assumption, but I've also changed assumption 5. So assumption 5 before was, you know, the predictions of quantum mechanics are accurate. Now I have to make some more physical or technological assumptions which go a bit beyond that, which is that, first of all, that human-level artificial intelligence is actually possible, okay? But I think, you know, this is very plausible now given where we are with AI, but also the assumption that very large scale and very fast quantum computation and communication is possible. And we'll see why that's important. Okay, so basically this is a very quick sketch of how it would work. So we're going to have, instead of just having two parties, and traditionally in quantum information, these are called Alice and Bob. Now we're going to introduce a third party who is the friend. So Alice, for example, has a friend called Charlie. Right? So there's Alice and Charlie. These lines here mean that there's actually a very big difference between distance between Alice and Charlie here and Bob, you know, maybe on the moon or something like that. Okay, what is Charlie? So as Charlie's profile pic suggests, he is actually a huge quantum computer running an artificial intelligence algorithm that is human level. Okay, we're going to imagine that that exists. We've made that proposition that that does actually exist. It's possible to do this, and also it's possible to have a big enough quantum computer to run that algorithm. Okay, and it's got to be really fast too. All right, to make the experiment at all feasible. All right, so how does it work? So first, so there's going to be an entangled pair of particles between Charlie and Bob, just as there was between Cole and Roe, right? And Charlie is going to measure, okay, I'm going to call it like her particle, meaning the one on Alice's side, and his particle, the one on Bob's side. So Alice first lets Charlie measure her particle, right? That's the particle entangled with Bob's. And he's going to, by this measurement, find out one of the properties of the particle. Okay, and by measurement, we mean in the sense that a quantum computer would measure a quantum input. Right? He's going to find out the logical value of the input, right, in a particular basis, and process that information, right? Have thoughts about, oh, I saw a 0. I'm feeling a bit down now. I saw a 1. Oh, I'm feeling great. Whatever. That's what we mean by a measurement. Okay. Then there's going to be a random choice by Alice, and either she's just going to ask Charlie what he observed, say, hey, Charlie, what did you observe? And he tells her, and she writes that result down. Or, this is the absolutely crucial thing, the other choice she could make would be actually to run Charlie in reverse, which means undoing everything that happened for the last second, say, in the interaction between the input and Charlie, which would undo his measurement, okay? This is what the prediction of quantum computing theory would say that it's possible to run a quantum computer in reverse because it's just running a unitary algorithm. It would undo everything, undo his measurement. The particle would no longer be entangled with Charlie. So then Alice can take that particle, make her own measurement on it in a different, measuring an incompatible property of it. And in that run, she would write that down. So she can't do both of these things, right? She either has to do one or the other because they correspond to incompatible measurements. And then we repeat this whole procedure many times and look at the correlations between Alice's results, recorded in this way, and Bob's results, which is just done in the normal way that he just freely makes a free choice of measurement on his own particle and measures whatever properties there, and then we look at those correlations. And what we find is that using these, I don't know if we, yeah, so the theorem then is that these correlations, which are predicted by these technological assumptions, then we're able to derive a different type of inequality from Bell inequality, but still show that they have violated, those correlations are going to be violated. Well, so first we derive the inequality from these assumptions, and then we show that this technology would enable us to violate those correlations, meaning that one of these assumptions has to be false. One of these propositions about the world must be false. They cannot all be true. Right? So just again, to remind you what they are, free setting, right? Relativistic causality, seems pretty uncontroversial. Absoluteness of observations for human beings, again, most people would believe in that. And then friendliness, which especially Eric Cavalcanti, my colleague, makes the point is that sooner or later we're probably going to be way outnumbered by these types of intelligences, so maybe it's good to adopt a friendly attitude towards them. Okay, so now which one should we give up? So now, again, let's ask Bohr. So now he can't say give up causal explanations, right? So I think you say, gee, now I don't know, right? Since giving up causal explanation is no longer an option. So I really don't know, but if I had to make a guess, I think that he would say, I'd probably give up friendliness. That's my guess. All right, there's no point asking Einstein because he was stumped by Bell's theorem even, but we can ask Bell, the ghost of John Bell, and I think I definitely know what he would say, which would be, I'm inclined to give up relativistic causality, because that was his attitude already for Bell's theorem, so I see no reason he'd change that for this new theorem. So he'd say, I tend to think that there really are faster than light causal influences. Okay, but you give any set of propositions and you'll find someone who will disagree with it. So for example, Sabine Hossenfelder, who many of you would know from her YouTube and inflammatory comments in various places, she thinks we should give up on free choice. Chris Fuchs thinks we should give up on absoluteness of observations, just to pick one example. And so Roger Penrose has a more interesting idea, I think, which is that he would say that it's the technological assumption which is false, for an interesting reason, that human-level artificial intelligence on a computer that can be reversed is impossible, because he thinks human-level artificial intelligence is something weird and irreversible and uncomputable that's happening in the brain, so it's just not going to be possible on a digital computer, and therefore not possible on a quantum computer. Okay, so those are some of the possibilities. Of course, the point of the theorem, maybe I'll go back, is that I think that there are, probably should have put it the other way, is that there are a lot of physicists, I think, who would just see nothing wrong with any of these. Right? You have a fairly, think that they understand quantum mechanics even, but would say that, yeah, I believe in all of these propositions, why should I give up any of those? Well, the answer is because provably it's incompatible with these technologies. And people are trying very, very hard to do these technologies, okay? So it would also be very interesting if these technologies were impossible. Okay, Right, so that gets me to my conclusion. So where I'm going to try to wrap up everything with the matrix again. Right. So in quantum mechanics, every physical quantity is represented by a unique matrix rather than a value. And according to the Copenhagen interpretation, these quantities have no definite values until they're measured. But John Bell showed that quantum mechanics gives rise to spooky correlations that give agents, in other words, experimental quantum physicists, superpowers. Right? And this is a bit like the agents in the Matrix movie. And for example, we could fool non-physicists into thinking that we have a magic matrix by utilizing entanglement. But this also lets us do useful things like quantum computing and quantum communication. And this then links into the far future vision that I have for where quantum foundations experiments are heading, is that we can use these quantum technologies to extend Bell's work by actually experimenting on an agent living in the matrix, right? In other words, simulated on a computer, in particular a quantum computer, and that our new theorem based on this idea shows that the world is even more puzzling than Bell's theorem has taught us. Thank you.
Thanks, Howard, for a great talk. So questions?
Thank you very much for the talk. So I'm planning ahead, and I see myself doing slides in maybe 50 years from now, where I need to invoke the ghost of Wiseman. And so my question is, what would
Can you hold it a bit further away? It's a bit hard to, yeah.
So I'm saying I see myself doing slides in 50 years and invoking the ghost of Wiseman. And so the question is, what would you give up?
What would I give up? Yeah, this is what people ask, yes. And I try to, I wouldn't give up this. I have an open mind. I think obviously what I would like to be wrong would be one of these, because that would be the most exciting thing, to actually do an experiment, try to build, for example, a very large scale quantum computer, which seems to be working fine, passes all the fault tolerance, thresholds, everything, but then you try to run an artificial intelligence algorithm on it and run it in superposition, which is essentially what the experiment requires, and then find that it just breaks somehow, right? It can't run the superposition, or it spontaneously collapses into one or the other. That would be, I mean, this is why I'm actually excited by the prospect of the experiments, because I think that's a real possibility. I don't think it's likely, just like Bell, I think, did not think it was likely that Bell experiments would show up anything different from quantum mechanics, but he thought it was worth trying. Okay, so I'm still dodging your question. So that's two answers: that what I would like to be wrong and what I would definitely not like to be wrong. If I really pushed, I'm probably inclined to actually give up friendliness, but it's none of them make me comfortable, put it that way. Yeah.
Right here. I'm somehow bothered by the absoluteness of observations somehow being a weaker assumption. My sense is, because the idea is that, like, my detector is not necessarily making absolute observations, but really when I look at it and comprehend it, it's absolute. Because when I look at this corner of my eye, my brain is just making up what's right there in my blind spot. And so, like, human cognition is, like, inherently unreliable. And somehow that seems like it throws into question any of these ideas, because our brains seem unreliable.
Yeah, I mean, yes, certainly we're not good at, yes. So for a Bell experiment, you would be, if you want to calculate the correlations, you're much more likely to want to store the data on a computer than ask a person to memorize 1,000 bits, right? So yes, we're not as reliable as the technology which we built. at least as it seems. But this is not really about reliability. It's not absolutely reliable. It's absolutely real. And this is in a metaphysical sense that I think for me, definitely for me as a human being, it's easier for me to believe, it's harder for me to believe that what I'm thinking is, in a sense, not real, is that maybe there are parallel versions of me who are thinking different things, or maybe that, yeah, okay, maybe it seems real to me, but for you, it's not real, right? I'm just some other physical system, and it just really isn't real for you, right? Just as you're really not real for me. So for me, right, the thoughts, and I guess this is why we called it a thoughtful local friendliness theorem, because we actually formulated it in terms of thoughts. So when we talk about observation, what we really mean is seeing something and thinking about it, right? So it's easy for me to believe that actually, yeah, I mean, that the detector in the laboratory, which we assume has actually reliably recorded something, maybe it really hasn't until I look at it. Maybe it's really in a superposition, everything is in a superposition until a person looks at it. That's more believable to me, or I'm more comfortable with that than the idea that I am in a superposition and we're all in some giant superposition. And yeah, does that make sense?
I have a question. Suppose I go back a billion years or a few billion years when none of us are around to make any observations. So I'm just asking, what would be the imprint or experimental signature that there is quantum entanglement?
Right. Yeah. Okay. Did entanglement exist before there was anybody there to do experiments? Yeah, I guess that depends on your interpretation. But I should say that, yeah, maybe this is an important thing to say, that when we say that these are a list of propositions about the world, this in no way says that, you know, if you believe these propositions, that these are the only things that you believe about the world. So you could, like, I could say, yes, I believe in absolute observations, that observations made by human beings are absolutely real. I could say, yes, I believe that proposition. And I also believe that dinosaurs were real, and, you know, the things on the other side of the universe that I can't even see yet, I believe that those are real. I could believe a whole lot of other things are real. Yeah, like just believing in this doesn't rule out believing in the reality of a whole lot of other things. But okay, coming back to the question of does entanglement, I mean, I guess one thing which I would say is that entanglement is, the existence of entanglement is only relative to defining subsystems which we're talking about. Right? So with that caveat, then yeah, if you say that, okay, atoms are, right, that, yeah, I'm going to talk about atoms as subsystems, then yeah, of course, there's been entanglement in molecules since, you know, I don't know, yeah, since a million years after the Big Bang, or whenever it was the molecules first formed. But were there Bell correlations there? No, I would say no. I would say that Bell correlations have not existed until at least, you know, in our part of the universe, until, you know, the 1970s or 80s, or whatever you want to put your threshold as to saying when it was actually done. Does that answer the question?
Sort of.
Yeah. Okay. Yeah. I could see that it's a subtle. There's subtle issues, but yeah, I'm sort of guessing what you.
Thank you.
Other questions? Okay, I had one question. So I think it's true that Bell was kind of influenced by Bohm's pilot wave theory, right? So in that theory, I mean, it's like hidden variables are there in some sense. So and which one of the propositions?
Yeah, that's a good question. So the question was about the theory of Bohmian mechanics, which was part of the story that did fill in the gap between EPR and Bohr in 1935. I didn't even mention PR, but I'm sure you all know about EPR. The Einstein-Bohr debate and Bell's theory in 1964, a crucial development in theory, which got very little attention at the time, was Bohm's work on what's sometimes called Bohmian mechanics now, which is exactly hidden variable theory. That was in 1953, I think. Yeah. Right, what does it say about our theorem? Well, let's go to Bell's theorem. Okay, so for Bell's theorem, what is violated in Bohmian mechanics is definitely relativistic causality, because Bohm's theory is, so Bell talked about it in his 1964 paper as, he talked about it, the grossly non-local feature of the Bohmian mechanics theory as is basically this violating a relativistic causality. And that's exactly what motivated Bell to say that was that a necessary feature or could we come up with some other hidden variable theory like Einstein thought, which would not violate relativistic causality. So I think that's the short answer for Bell's theorem. So for our new theorem, it's also the case that Bohmian mechanics violates this. An interesting question is whether Bohmian mechanics respects friendliness. And that's, I think that's a very interesting question because it might depend on which version of Bohmian mechanics you're looking at and what your quantum computer is actually built from. So I think that's a very interesting, subtle point that we're planning to write a follow-up paper sometime talking about issues like that. Because in Bohmian mechanics, it's actually positions of particles moving in three-dimensional space which define what's real. And so the question is, do the positions of those particles actually correspond to thoughts of an artificial intelligence? Like if you have an artificial intelligence running on a quantum computer, are the thoughts of that quantum computer reflected in Bohmian particles moving in three-dimensional space in a particular way? And if they're not, then we'd have to say that according to that theory, the reality of the thoughts of that artificial intelligence is not the same as the reality of the thoughts for a human, in which it definitely is the case that the motion of Bohmian particles, in describing, my electric pulses in my brain, does, we believe, most people believe, reflect what I'm actually thinking. So again, a complicated answer. Thanks. One more question.
Hello. Yeah. Hi. Thanks, Howard, for the talk. So my question is this theorem? Are you considering any particular interpretation of the quantum mechanics to prove this theorem, or it is just a bit more subtle than that?
Yeah. No. So it's supposed to be like Bell's theorem. Not make any assumptions about the particular interpretation. So quantum mechanics is not mentioned in any of these, what I call metaphysical assumptions. The only place that quantum mechanics enters is in the assumption that large scale and fast quantum computation and communication is possible. So it is meant to be, it's meant to be agnostic about any particular interpretation of quantum theory. But as I was trying to intimate with the, asking this question about what we should give up, there are various pre-existing interpretations of quantum theory which would be inclined to give up different ones of these assumptions, right? But then I think there are also plenty of other interpretations, in inverted commas, of quantum mechanics which don't give up any of those. And I think this is a challenge to all of those interpretations that, no, you should actually ask the question of your interpretation, which one of these does it give up? And if the answer is none of them, then you've got a real problem.
Okay, so if there are no other questions, let's thank Howard for really fantastic. Thank you. So, on behalf of ICTS, I'd like to present Howard with a small gift.
Thank you. Well, okay, thank you very much.
Some high tea outside, so everyone is welcome to join.